you've worked with degrees your whole life, so I think you'll probably be fairly familiar. So let's start right here with this first angle right here. What degree would that be? 30. And the next one, 45, and then 60, and then up here we're 90, right? We're a quarter of the way around the circle at 90, right? This is called your first quadrant right here. Okay, and then we're at what? 120, 135, and 150. All right. And then down here we're at 180 degrees. So if we had an angle that started here and rotated all the way over to here, 180 degrees, that's called a straight angle. All of these first quadrant angles are less than 90 degrees. These are called acute angles. An angle that's between 0 and 180, excuse me, greater than 90 but less than 180, these angles are called obtuse angles. Those are all from geometry, right? Many years ago, probably, for many of you. So this next one, what's the angle here? 210, and then 225, 240, 270. Nope, 270 is down here, yep. And 300. So we know that Brad and Leah did it. Someone else other than Brad and Leah? Next one. 315, 330, 360, and 0 are the same angles. This has rotated full circle all the way around. Okay. Every time you're working with degrees, you must absolutely put in the degree symbol. Always. Or write the word degrees. All right. So if I'm asking you to find the sine of 40 and you mean it to be 40 degrees, you've got to put degrees in because the sign of the number 40 is very different without the degree symbol. All right. So always use the degree symbol. All right, and then our intercepts, this is a unit circle, which means the radius from the center to any point on the circle is 1. So all these radii all the way around is 1. So this is, what's this point? 1, 0. And then at 90 degrees, we're 0, 1. And at 180, we're negative 1, 0. And at 270, we're 0, negative 1. 0, 90, 180, 270, 360, and then any multiple of that, those are your quadrantal angles. Quadrantal. So 0, 90, 180, 270, 360, and then we could just keep cycling around, right? We could add 90 to 360 and get 450. We can just keep going and going. It's infinite. In trig, your angles move, and there's an infinite number of them. And geometry, they're static. They're just the union of two rays. So it's a lot more interesting things going on in trig than in regular old Euclidean geometry anyway. Okay, so let's talk degrees for a minute. And there's going to be a lot of new terminology. Maybe not new for some of you, but it will probably be new for many of you. So an angle, we can define it as two rays. And what is a ray? A ray is a part of a line. It has one endpoint, right? And then it continues on forever and ever. So this is called a ray. So you have the union of two rays with a common endpoint. That endpoint is called the vertex of the angle. The measure of the angle is the rotation. How much rotation is there between taking this initial side and rotating it in a counterclockwise and then stopping to your terminal side? This is called the initial side. This is called the terminal side. So it's that Amount of rotation, or how much it opens or how much it turns, is the measurement of the angle. We use theta. Theta is a way of measuring the angle. That's the Greek letter theta. Well, here are our popular Greek letters. Theta for measuring an angle. Sometimes we use alpha, which looks like that, alpha. Sometimes we use beta, which looks like that, gamma, which looks like that, and then phi, the most common way is that, but it can also look like that, one or the other. So those are typically the 5 Greek letters we use to denote the measurement of an angle. So this idea of having an initial side and rotating that, stopping, that's called your terminal side. So when we measure angles on a circle, we measure angles in what's called the standard position, and that has a meaning. The standard position says your vertex is always at the origin in both of these cases. You're going to take your initial side and rotate it. In this case, we got a little baby alpha here. We're going to rotate it to some point, some other quadrant, perhaps in this case, the second quadrant. So the initial side gets rotated in a counterclockwise manner. We say that this angle is positive. Whenever you rotate your angle in a counterclockwise, it's positive. If you start at the origin, and notice the other thing about standard position is your initial side always lies along your positive x-axis. So if you meet those two conditions, your vertex at the center, and you see here this is a different color, right? My initial side is blue, always lies along the x-axis. And then you rotate it now clockwise to your terminal side. In this case, it's in the third quadrant. Now this is called theta. That is considered to be a negative angle. So you would, if you were working in degrees, this would be negative. Well, let's take a guess as to what we think each of these angles might be. We don't know exactly. So here's alpha. What do you think might be the measurement of alpha here in degrees? 103. I think 103 would be closer to maybe something like this, Jackson. Yeah, because look, if you do it halfway, right? Halfway, it's going to be 135, right? So I think alpha might be a little closer to like 120, 118, 122 than 103. Okay. What about this angle? This is theta. What do you think there? So if we were rotating just here, it would be negative 90, right? And then it looks like we're going another 20 or so, right? So maybe, oh, negative 110, 115, somewhere around there. Right? So negative angles rotate clockwise, positive counterclockwise. Yep. Oh, look what I did. Can't forget my degrees. Yeah, go ahead.
So we're not doing 360
What are you talking about? This one right here?
Yeah.
You could think of it that way if you wanted. 360, what would you be subtracting? No, because you're not measuring this way, which would be the, when you subtract the 360, you'd be getting this amount, right? Well, if you subtract 3, how are you thinking about that, Shane? I'll tell you where the subtracting 360 comes in, because we're going to be doing that in just a quick second. All right? All right. All right. Then we've got this. So let's see what have we taken care of so far. Let's see. We've got initial side down, terminal side down, standard position, negative angles, degrees. This is the one we're going to talk about now. Co-terminal. Kind of sounds scary, doesn't it? Like when you're terminal, it's like co-terminal. Ooh. So co-terminal angles end up in exactly the same spot. The initial side gets rotated, and then sometimes you can do, but the point is they end up with this at the same terminal spot. The same terminal side is in the same position. It's coterminal. So two angles with the same initial and terminal sides, they have the same initial and terminal sides, but the different amounts of rotation around the circle. Those are called coterminal. So let's take a look at this first one. Here's our first rotation right here, 55 degrees. So I took this initial side and I rotated it right to here, 55 degrees. That angle is the same as starting here and going a complete rotation, complete rotation around. So I'm at 360, right, when I get to here. And then I continue another 55 degrees. 360 and 55 is 415. I end up in exactly the same spot. So 55 and 415 are called coterminal angles. Now, if I go the other way, I start here. I'm at negative 90, negative 180, negative 270. And then what happens is I add 35 more degrees, negative 305. I'm in exactly the same spot. So all three of those angles are called coterminal. Okay, so the initial side and the terminal side are exactly the same in the same position. It's just you do a different amount of rotations, and sometimes you change the direction of the rotation. So how would we get a coterminal angle? So you're going to get a coterminal angle by increasing or decreasing. So by increasing or decreasing, so adding or subtracting, 360 degrees or a multiple of 360. 360 degrees to whatever your initial angle was in standard position. So our initial angle here was 55 degrees. And to get 415 degrees, I added one multiple of 360 degrees, and I got 415. I could add 3 multiples if I want. And then to get negative 305, I would start with 55 degrees and I would subtract 360 degrees. This was what Shane was thinking about earlier. If you subtract 360 from 55, you get minus 305 degrees. Okay. So if we were going to try to make a little formula for coterminal angles, it would look like this. Theta plus or minus some integer multiple, like k be an integer, some integer multiple of 360. So if k is 4, you would have 4 rotations in either direction, right? You could either increase it by 4 rotations of 360 or decrease it by 4 rotations of 360. So at your seats, and check with your neighbors, find 2 angles, one positive and one negative, that's coterminal with 55, but not one of these 2 that I have up there. Come on. What is it? 3,295 degrees, and that's equal to 55 degrees plus how many multiples of 360? 9 multiples of 360 degrees. Okay. One more. 775 degrees. And how many multiples of 360 was that? 2. Okay. How about some negative angles at a coterminal? 65 degrees, which is 55 degrees minus 2 360s. Okay. One more. Negative 3,185 degrees, which is 55 degrees minus 9 times 3,360 degrees, right? Okay. All right. All right. So here's the scoop, folks. Degrees, you're just really familiar with degrees because you've been working with them your whole life. And when you think about it, where is my picture? So if I was looking at a circle and I asked you where 1 degree is, how would you figure out 1 degree? How do you know where 90 degrees is? How do you know that 90 degrees is here? All right, then how about 60 degrees? How do you know where it is? What are you basing its position upon? The degrees of 0. Okay. 2/3. Of what? 2/3 of 90. Oh, so you're thinking just right triangles. How about if I said 270 or 240 or whatever? What fraction is 90 degrees of the whole circle? Thank you. It's a quarter of the way around, right? Right. So you go a quarter of the way because 90 over 360. So 90 degrees is 1/4 of 360 of a full rotation, yeah? Okay. So that's how if I separated the circle into 4 pieces, you can find your 90 pretty easily. So what would 1 degree be? Yeah, 1/360th of 300. So it's probably the width of my pen is too much, but it's a really small piece, right? That's your 1 degree. Okay. So that's what degrees do. And why 360? Has anybody ever like looked at things historically, mathematically? Why 360? Why not 500? Yeah, so think about that. How many days in a year? 365 and a quarter, right? Yeah, all right. So it's pretty close to the number of days in a year. There is something astrologically that has to do with like 60ths and 360s. And in ancient times, we had a system, I think it was Babylonian, that was base 60, not base 10. They had 60 symbols. So I don't know the answer. These are just some of the ideas of where this 360 degree idea came from. But as you can see, it was created by human beings. It's nothing intuitive. It feels intuitive because you've been working with it your whole life. Okay. Today, and I meant to get the tire. You know that tire you always see in the studio in there? I meant to get the tire, but I've had problems with my wrist and trying to take string around a tire to do this. So Ian gave me a PowerPoint that does the same thing. Today, we're going to talk about a new measure for an angle that's not degrees. It's called radians. So I just want to give you, and this is why I said you can flip over your paper and draw these little circles on now. So let's see if I can find the magic pen here. It's the magic. Can I get that up there? All right. All right. So let's say this circle, what we won't call it the unit circle yet. We'll just say this circle has radius r. Now let's suppose I drew an angle. Let's call it theta. And if you think about this extending through the circle, do you see how it sort of cuts out a little piece, a little arc of that circle, a little length? Okay, we're going to call that length S. Now, I've chosen theta so that this cuts out this little length. This is, if I took this, like if it was a piece of string, I could straighten it out. It's a linear measurement, this arc length. This is called the arc length of the circle. S is called the arc length. And it's determined by this angle. All right. Now, what would you tell me about the length of S compared to the length of the radius? What would you tell me about that right now? As I've no, yeah, I just want you to compare this length with this length, that's all. Just a comparison. It's smaller, right? Yeah, all right, that's all I was looking for. It might be half of it, you might be right. So right now, S is smaller than R, right? The length of S is smaller than the length of the radius, all right? How about if I do this? All right, now we're going to take away this angle. This is where I should have used my magic pen. All right, so now our angle goes to here, and that's theta. And now what does S look like? S is now this portion of the curve, right? This length. That's S. What can you tell me about S now? It's bigger. And really, technically, I should be saying the length of S is smaller than the length of R, right? But, all right. So, I was talking to Ian, and he has a little way of saying this, which I really love. So, if you think about this original one right here, this, let's call this S1, and we'll call that S2. He equates it to like Goldilocks and the Three Bears, right? Because Goldilocks, if you're familiar with this, goes in and tests out the different beds, right? And one bed was a little bit too small, and one bed was just a little bit too big. And then there was what? The bed that was perfect, right? So what if we could find the angle that was perfect? Yes. So here we have R, and we would find the angle that the length along this arc was perfectly matched. That distance was perfectly matched to the radius, so that the length S now was exactly equal to R. So it'd be like taking the radius and literally placing it along the arc, the outside of this circle. Right? So we're trying to find that angle theta so that this portion of the circle has exactly the same length as that radius. And when we find that perfect angle, we're going to say its measure is 1 radian. 1 radian. And in the word radian, can you see the word radii? Radii is the plural of radius, or you could say radiuses, right? All right. So 1 radian would be like going the distance around your circle of 1 radius. What would a circle of 2 radians look like? Where do you think I'd end up if this was my radius? What quadrant would I end up in if I placed 2 radiuses? Second. All right. So let's try that. Well, let's have the PowerPoint do it for us. So you can copy this on your paper if you want some version of this. So what is a radian? All right, a radian is an angle measurement, and it's given by a ratio. It's the length of the arc divided by the length of the radius. When the length of the arc, there we are, that's that red circle I've been doing, that red linear, equals the length of the radius, the angle has a measure of 1 radian. Okay. So now imagine we got the same circle, the same arc length, the same radius. Think in your mind where 2 radians would be. Just in your mind, see if you can see where it is. Or place it on your circle on your paper. So here's when the length of the arc is twice as long as the radius, the angle has a measure of 2 radians. All right. The big question is 3 radians. So in your mind, try to picture 3 radians. Is it going to bring us before this point, after this point, right on this point? When the length of the arc is 3 times, well, it's pretty darn close, right? At least Jackson took a guess. When the length of the arc is 3 times as long as the radius, the angle has a measure of 3 radians. Now here's the clincher. It's so cool. When the length of the arc is pi times as long as the radius. What's pi roughly? 3.14. So it's pretty darn close to 3, isn't it? Right? So Jackson was pretty darn close, wasn't he? All right. So when the length of the arc is pi times, so I've got pi radians, radiuses, right? You got 1, you got 2, you got 3, and now you got pi of them. Then what's the length of theta? What's the measure of theta going to be? No, in radians. Pi radians. Yes, pi radians. Isn't that cool? I was going to do that with the bicycle wheel that's in there because from the center of the hub to the outside is roughly a foot. And I was just going to place it with like strings. But why? The point here is that you can take these distances along your circle and you can stretch them out. It's soon going to become an x-axis for you. But right now we'll leave it there. So that's how we measure angles now based on the length of the arc of a circle. It's a portion of the circle. Let's see what else I have here. Okay, so this is how we actually create the angle measurement. Theta is the length of the arc divided by the length of the radius. Okay. The cool thing is when we have a unit circle, the radius is 1, right? So the length of the arc, S, is going to be exactly your measurement, your number of radians for the angle. Okay, as long as it's in standard position. That's what's really cool for the unit circle. Radius 1, 0, 0, 1, 0, length of the arc divided by 1. The radian measure of an angle for a unit circle is equal to the length of the arc, and this is just a fancy word. The length of the arc it subtends. It's just the length of this arc that gets cut out, intercepted, cut off by that angle, or subtended by that angle. That's just a really fancy math word for the angle that goes right through the circle and cuts that piece out, that little piece of the circle. Okay? All right, so let's go back to our, if I can figure out how to get out of it. It's been so long. All right. What's the ratio now? So here's the length of the arc, S, all the way around the circle. What's the ratio of the circumference of the circle, which is 2 pi r, to the radius? What's that come out to be? 2 pi. Is 2 pi a constant? Yes. This is like glorious news. Glorious. That tells you that that ratio is not dependent on the length of the radius. It only depends on the angle, the measure of the angle, because your radii are always going to cancel here. It's always constant. Just like your straight line, you have a constant rate of change. I'm looking for my packet. I don't have it. Okay. So let's take a look at, and this is getting back, I think, to something Shane or someone at that table said earlier. What if we changed the length of the radius of a circle? So and this is right out of your book. So if you want to just pay attention and you can copy it out of your book, it's pretty similar to what's in your book. So my smaller inside circle has a radius of 2. My outside circle has a radius of 3. So let's first figure out what the circumference of my smaller circle is. So the circumference of my smaller circle is 2 pi times 2, which is 4 pi. That's the circumference. And the circumference of my larger circle is 2 pi times 3, 6 pi. All right. So that's just dealing with the circumference of the circle. Now suppose I take a 45-degree angle and I cut right through the circle. Right? I extend that angle all the way out so it cuts a portion of the circle out. So let's take a look at the arc length based on this angle right here. Can you all see that this length, regardless of whether it's on the smaller circle or the larger circle, is 1/8 of a full rotation? Okay, because look what 45 degrees does. It divides each quadrant into 8 pieces, right? So this piece here can duplicate itself 8 times around the circle. And this piece can duplicate itself 8 times around the circle. So the arc length of the smallest circle, S, the arc length is 1/8, right, of the entire length. And what did we just say the entire length was around the circle? 4 pi. So that's 4 pi over 8, and that's pi over 2, or you could write it as 1/2 pi. So this is the length of that arc right there, 1/2 pi. So now let's find the arc length for my larger circle. Let's make it a little different color, blue. So let's find the arc length that's blue, my larger circle. It's 1/8 of the total distance around, which is 6 pi, right? Which is 6 pi over 8. And when I reduce that by dividing top and bottom by 2 over 2, I get 3 pi over 4. So that's the length of the blue arc. All right. Now this is where all the fun comes in. If I take those arc lengths, remember what we said about radian. A radian measure was the ratio of the length of the arc divided by the length of the radius. So let's take these arc lengths and divide them by the length of the radius. So for the smallest circle, the length of the arc was 1/2 pi. And if I divide it by the radius, which is 2, what do I get? And this is where pi over 4, thank you. Or you could say 1/4 pi, because half of a half is a quarter. For the larger circle, we get the length of the arc was 3/4 over 4, and our radius was 3. So in case you need a little work with division, dividing by 3 is the same as multiplying by 1/3, right? Look what happens. You get pi over 4, or 1/4 pi. So that tells you that this 45-degree angle is pi over 4 radians. That's the equivalent of 45 degrees. It's pi over 4. So as you can see here, when I took this ratio, it didn't matter whether I was on the circle with radius 2 or the circle with radius 3 or the circle with radius 10. It doesn't depend on the length of the radius, just the angle. Similarly, whether you're looking at a 60-degree angle, doesn't matter whether you're on a small circle or a large circle. The angle is independent of the length of the radius. Radian measure is the same way. So 45 degrees, we're now going to start calling this angle pi over 4. Because pi over 4 is what you get when you take this arc length and you divide it by its radius, or this arc length and divide it by its radius. A unitless measure, that's the ratio of two lengths, pi over 4. All right, so we just said that, well, I'll keep going. It takes a little while to digest. So here's your definition of a radian measure of an angle. The radian measure, most of us just use theta, is the length of the arc, S, over the radius. That's a radian measure. And we just did that and got pi over 4. And we saw that pi over 4 was equivalent to 45 degrees. We also noticed that if we are on a unit circle, we just saw this, the radius is length 1, so your radian measure is exactly the same as your arc length measure. That's why we love working with the unit circle so much. All right. So this is a different PowerPoint presentation I want to show you. And if you want to do this on, so draw one of these circles that I had here and think about dividing it into 24 equal pieces. 24 equal pieces. So how many sections will there be in each quadrant here? 6. Okay, so we're going to divide it into 6 equal pieces. So do that on your paper however you want. Divide it into 24 pieces. You don't have these circles, so you just draw them on the back of that blank piece of paper. Okay, why 24? That's the big question. And not because I like Kiefer Sutherland either. All right, why 24? How many degrees would each of those angles be for each of these 24 sections? Anybody figured that out? Yeah, if you take 360 degrees and you divide it by 24, you get 15 degrees per segment, right? Why 15 degrees? Well, here's a little type of thing that might help you with the future as you're trying to go around this unit circle. This again is from someone that Ian knows. So look, we're really familiar with these middle three, 30, 45, and 60. When you convert 30, 45, and 60 to radians, which we'll do in a minute, look at it. It's pi over 6, pi over 4, pi over 3. It's like, huh? How am I going to remember that? It's a little like weird. This like doesn't seem to be a pattern. However, when you divide each one of these circles into 15 degrees, it goes 15, 30, 45, 60, 75, 90. 105, 120, 135, 150, 165, 180, all the way around, right? We don't really care about 15 and 75. They're not that important. But 15 degrees is equivalent to pi over 12 radians. So if each one of these increases by pi over 12, think about this. Pi over 12, 1 pi over 12, 30 degrees is next. 2 pi over 12, which is what? Reduces to what? Pi over 6. Next one, 3 pi over 12. 3 pi over 12 reduces to pi over 4. 4 pi over 12 reduces to pi over 3. We don't care about that one. It's 5 pi over 12. 6 pi over 12, pi over 2. We don't care about 105. 120 is 6, 7, 8 pi over 12. 9 pi, 10 pi. We don't care about 11. 12 pi over 12 is pi. So if you're ever like trying to recall it for yourself, and this is really cool, it's a little animation. You can just sort of think about what number of pi over 12 you are in the quadrant. It doesn't take long because you know you go 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10, and then you just reduce it. So these beautifully brilliant colored segments here are the important angles. And if you're trying to remember, is this one pi over 6, or is this one pi over 6, or is this one pi over 3? Just say 1/12, 2/12, 3/12, 4/12, 1/3, 1/4, 1/6 with a pi. See? 6/12, 7 we don't care about. 8/12, 9/12, 10/12, and then we go down to 12/12. We don't care about 7 and 11. So it's just a little way to help you remember once you reduce them. I thought that was pretty neat. Oh, good. Yeah. Huh?